All right. So what we're going to do today is Chapter 17, Part 3. And here we go. Okay, so now we're all set up with the notes. So this is the last part of Chapter 17, Part 3. And we basically have done everything we need. So a couple things to remember. The key, first off, we are dealing with sampling distribution models. So the key is the sample statistic itself is a random quantity. So if you recall, we're going to be looking at two different things. We're going to take a look at sample means and sample proportions. Those two things vary depending upon the sample. They change. That's what they mean. They vary. So we can't know what our statistic is because it comes from a random sample. So fortunately for the mean and proportion, the CLT tells us that we can model their sampling distribution directly with a normal model. There are two basic truths about the sampling distribution. Sampling distributions arise because samples vary. Each random sample will have different cases and so different value of the statistic. Although we can always simulate a sampling distribution, the central limit theorem saves us the trouble for means and proportions. Now, very key, our parameter does not vary. Our population mean is fixed. This does not change ever. And our population proportion is fixed. This does not change. So this is a true value about the population that is not changing. We often never actually know this value. We often want to try to guess what that value is, okay? There is one difference. On election day, it's one of the few times we actually do get to find out what that parameter is. At the end of the day, we are able to count all votes that are tallied, and we actually find the true population proportion. And that's how we can compare the p-hats, how the posters get, to what the true p is, what happens on election day. So here's the idea of the sampling distribution. This is the population. Okay, notice the population is skewed to the right. It has a population mean and it has a population standard deviation. Okay. Okay. I take a sample, I get a sample mean. Here's sample 1. And I get a sample standard deviation. I take another sample. Here's sample 2. And I get a different sample mean and a sample standard deviation. And I take another sample. Now, if you take a look at each one of these samples, you notice they kind of look like the population. They're all skewed right, and they all look different. Now, what happens if I graph the sample means and just the sample means of each of these samples? Well, it turns out I get a roughly normal model out. This is the sampling distribution. Okay. I just graph the means, okay? Now, what's also cool is the center of the sampling distribution is the true population mean, which is so awesome. And it has a standard deviation of sigma, the population standard deviation, divided by the square root of n. And lastly, AP tip. The vocabulary in this chapter is daunting, but don't overthink it. Okay, the AP test will ask you about the mean of a sampling distribution of sample means. So when describing the shape of a sampling distribution, remember to say it's approximately normal. Nothing is perfectly normal. Okay, and omitting the word approximate will cost you rubric points. All right, example 1. So statistics from Cornell's Northeast Regional Climate Center indicate that Ithaca, New York, gets an average of 35.4 inches of rain each year with a standard deviation of 4.2. So mu equals, okay, I'm sorry. All right. So couple things we are going to do here, okay. So basically, yeah, our mu is 35.4 inches, and our standard deviation is 4.2 inches. Assume a normal model is appropriate. So that's a very important statement. So A, during what percentage of years does Ithaca get more than 40 inches of rain? Okay. All right, so of years, okay, we want to know a couple things. We want to model a sample. So step one is we need a mu of my sample means, and that happens to be my mean of my population. My standard deviation of my sample means is equal to my standard deviation divided by the square root of n. Okay. Now, in this problem, it turns out we are just looking at what percentage of these years get more than 40. So we're going to assume that this is just going to be over a year. Okay, this happens to take 1 year. So we'll get the same standard deviation, 4.2. So the probability that x is going to be greater than or equal to 40 inches is going to equal the normal CDF of 40, comma E99, comma 35.4, comma 4.2. All right, then let's do that in a calculator. So we have second distribution, normal CDF, and we're going to do 40, enter, second E99, and then we have 35.4, and then we have 4.2, and then we have paste, and then we get the answer, and that is 0.1367. All right, so I'm going to say 13.67%. Okay. Now, less than how much rain falls in the driest 20% of years. So if we're trying to draw a picture here, here's our normal model. Here's our mean at 35.4. And we want to know what value here is going to give us the driest 20%. So this is an inverse norm problem. Okay, and we want the lower 20%. We have a mean of 35.4, and we have a standard deviation of 4.2. So second distributions, inverse norm, and we want 0.20. We want 35.4, and then we want 4.2, and then we get our area, and our value is going to be 31 let's go 9 inches of rain. And there is our answer. All right, now C, a Cornell University student in Ithaca is there for 4 years. Let Y represent the mean amount of rain for those 4 years. Okay, now we have a sample size. N is just 4. All right, so we have a sampling distribution. So mu of x bar is the same as the mean, 35.4. And sigma of x bar is definitely going to change, 4.2 over the square root of 4. So that's going to give us 2.1. Okay, so this is going to be modeled with the normal model with the mean of 35.4 and a standard deviation of 2.1. All right, D. Now, what's the probability that out of those 4 years, so again, I want a sampling distribution, the average is less than 30. So the probability that x bar is less than or equal to 30 inches is going to equal the normal CDF of 30, we want less than, so we want negative E99, comma 30, comma the mean, 35.2, 4, comma 2.1, different standard deviation. All right, let's plug that in. So second distribution, normal CDF. We want negative E99, upper is going to be 30, we want 35.4, and then we want 2.1 as a standard deviation, and we paste it, and then we get the answer of 0.005. Okay. All right, how about example 2? So some business analysts estimate that the length of time people work at a job has a mean of 6.2 and a standard deviation of 4.5. So it has a mean of 6.2 and a standard deviation of 4.5. Explain why you suspect this distribution may be skewed to the right. Okay. All right, so here's my first thought of this, why this might be skewed to the right, and I might say the following. Some people work for longer than the mean, okay, plus 2 or 3 standard deviations. Okay. Part B, explain why you could estimate the probability that 100 people selected at random had worked for their employers an average of 10 years or more, but you could not estimate the probability of an individual has done so. Okay, so here would be that answer. The CLT says that Y bar is approximately normal for large sample sizes, but not for samples of size 1, which means an individual. Okay. All right, example 3. One of the museum's phone volunteers sets a personal goal of getting an average donation of at least $100 from the new members she enrolls during the membership drive included in example 12. If she gets 80 new members, and they can be considered a random sample of all museum's members, what is the probability she will achieve her goal? Okay. All right. So if we look back at example 12 in our notes, all right, and I'm going to pick that up real quick. Example 12 in our notes. Okay. All right, which is going to be museums, trying to find museums. All right, so we're trying to find which one that corresponds to. I even remember this one. Oh, I think I switched this around. I'm sorry. So this is the example here. So a museum offers several levels of membership as shown in this table. Okay, so it looks like we actually need to complete this problem before doing this problem. Okay. All right, so we need to find the mean and standard deviation from these donations. Okay, so we have all of these individuals and we have the percentages. So what I would do here is go to Stat, Edit, and we would do clear my L1, and we would clear my L2. So in L1, we're going to put 50, and then we're going to put 100, and then we're going to put 250, and then we're going to put 500, and then 1,000. And the probability, so we have 0.41, we have 0.37, 0.14, and 7, and 1. Oops, 0.07, 0.01. All right, so then we quit. Go to Stat, Calc, 1 bar stat of L1, frequency list is L2, and then we're going to go to Calculate. All right, so the mean is going to be 137.50, and our standard deviation is going to be 148.56. So B, during the annual membership drive, they hope to sign up 50 new members each day. Would you expect the distribution of donations for the day to follow a normal model, and explain? Okay. So why would I or why would I not? Let's check this out. Okay. So I would say no. These 50 members will probably make donations typical of the current member population. And that's skewed to the right. So if they take one sample, it's going to look something like the population. And if you notice, our population is skewed to the right. Okay, now consider the mean donation of 50 new members each day. Describe the sampling model for these means. Okay, so now we do this for each day with a sample size of 50. So now our N is 50. All right, so our mean of a sampling distribution is going to be the mean of the population, 137.50. And our standard deviation is going to equal the standard deviation divided by the square root of 50. So this is going to be approximately normal with the mean of 137.50 and a standard deviation of 148.56 divided by the square root of 50. All right, now we can go back to number 3. All right, so of the new members, they set a personal goal of getting a donation of at least $100 from the new member she enrolls, okay? If she gets 80 new members and they can be considered a random sample of all the members, what's the probability she will achieve her goal? Okay. So from the previous page, we know we have an approximately normal distribution with a mean of 137.50, okay, with a standard deviation of 16.61. This should be slightly changed. So our standard deviation should be 148.56 divided by 80, square root of 80. And we want to know what's the probability we get at least 100. X is greater than or equal to $100. So that is going to be the normal CDF of 100, E99, 137.50, 148.56 divided by the square root of 80. All right, so second distribution, normal CDF. And then we have 100, and we have E99. And then our mean is 137.5. And then our standard deviation is 148.56 divided by the square root of 80. And then I hit paste. And there we go. And we get, okay, 0.988. So about a 98.8% probability that this happens. All right, and then that is your notes.